Now, in the previous lecture, we have seen exponential functions and sinusoidal functions with some examples. The next topic is singularity functions. So, singularity functions are also continuous time functions. So, we'll see singularity functions. So, what are singularity functions? Singularity functions are the functions which are related to each other, by integrals or derivatives. That is, one function can be obtained by integration or differentiation of the other function. Okay, that is how these singularity functions are related. So, singularity functions are used for mathematical description of signals having discontinuities. Okay, that is, we already have seen what is a discontinuous function. That is a function whose value is changing suddenly at some instance of time. That is, there is a sudden increase in the amplitude or there is a sudden fall down in the amplitudes. Okay, so the signal whose amplitude is suddenly changing is said to be a discontinuous function, and it is having discontinuities at some instance of time. So, for mathematically describing such signals, I am making use of singularity functions. So, let us see some of these singularity functions. The first one is unit step function. So, as the name implies, it is changing in a step manner. Okay, if I represent the unit step function as u of t, the amplitude of the signal is equal to 1 for t greater than 0, and it is equal to half for t is equal to 0 and 0 for t less than 0. And if I draw it graphically, that is u of t drawn against time. Okay, so if this is equal to 1, so for t less than 0 it is 0, this is my t is equal to 0, it is 0, and at t is equal to t greater than 0, it is suddenly jumping to 1 and it remains at 1 up to infinity. Okay, so at t is equal to 0, what is the amplitude? It is equal to 1 by 2. So this is what is unit step function. So there are different functional representations of this unit step by different authors or in different textbooks. Let us see all these different notations. Okay, that is u of t is equal to 1 for t greater than or equal to 0, 0 for t less than 0, or we also have u of t is equal to 1 for t greater than 0, 0 for t less than or equal to 0, or we have one more notation which is u of t is equal to 1 for t greater than 0 and 0 for t less than 0. So all these notations are equivalent. Okay, so different authors or different textbooks have these notations. So all these are equivalent. So what is unit step actually representing? It is representing some common action in some physical system where the signal is changing or it is switching from one state to another state. For example, I have a capacitor, okay, which is connected through some switch. Okay, this is my capacitor C, and it is connected to supply voltage or battery. Let us say my battery voltage is VB. This is my switch, okay, and this is my resistance, and this is the capacitor. If I represent the voltage across the capacitor as V of t, okay, so let us say the current flowing through this circuit is I of t. Then when I close the switch at t is equal to 0, okay, I am closing the switch, there is a sudden change in the voltage. When the switch is open, the voltage is 0. When the switch is closed, the voltage is suddenly rising to VB, okay. It is called, this is just like a step variation, okay. So unit step function represents some common action in a physical system where it is switching from one value to another value, okay. Now the current through this circuit is changing exponentially, and it is exponentially decreasing. That is given by VB by R into e power minus t by RC, and because the switch is closing at t is equal to 0, after t only the current is flowing. So I can multiply it with a unit step function, because u of t is equal to 1 for t greater than or equal to 0. So I can multiply it with unit step function. Why it is decreasing exponentially? Because as the voltage is building, the voltage across this is decreasing. So the current keeps on decreasing. And the voltage across the capacitor keeps on increasing exponentially, which is given by Vb into 1 minus e power minus t by RC, and it is also starting at t is equal to 0. So I can multiply it with the u of t. So, unit step function represents a common action in physical systems, like in this case where it is switching from 0 to a voltage of VB when the switch closes. Okay, and the second important singularity function is signum function. Signum function. So, the signum function defined by Sgn of t is equal to, it is equal to 1 for t greater than 0, 0 for t is equal to 0, and minus 1 for t less than 0. That is, it is positive for t greater than 0 and it is equal to 1. That is, for positive time it is positive, for negative time is negative, and it is equal to minus 1, and it is 0 at t is equal to 0. So I can draw graphically the signum function as Sgn of t. So if this is 1 and this is minus 1, okay, so it is 1 for t greater than 0, minus 1 for t less than 0, and 0 for t is equal to 0. So signum function can also be written as 2 into u of t minus 1, where u of t is the unit step. Because u of t is equal to 1 for t greater than 0, so 2 into 1 minus 1, it is 1 for t greater than 0. At t is equal to 0, u of t is half, so 2 into half is 1, 1 minus 1 is 0. For t less than 0, it is 0, so 2 into 0, 0 minus 1 is minus 1, okay, this is minus 1, okay. This is what is signum function. The third important singularity function is unit ramp function. Unit ramp function. So unit ramp function represented as R of t is equal to t for t greater than or equal to 0, 0 for t less than 0. That is, the ramp function is increasing in proportion to time. That is, R of t is 0 for t less than 0. From t0, it is increasing linearly with respect to time with a slope of 1. T can be written as 1 into t. So what is the slope? Slope is equal to 1. So that is why you call it as a unit ramp function. So unit ramp function can also be written in terms of unit step as t into u of t, because u of t is equal to 1 for t greater than 0. T into 1 it is t. it is 0 for t less than 0. So t into 0, it is 0. So r of t can also be written as integral minus infinity to t u of tau d tau. It is r of t is equal to integral minus infinity to t u of tau d tau. So let us check how this expression is valid. That is, if I want to find r of 1, then it is equal to integral minus infinity to 1 u of tau d tau. Minus infinity to 0, it is 0. From 0 to 1, it is 1. So integral 0 to 1 u of tau is 1. So 1 into d tau. So 1 into d tau is tau, integral 0 to 1. So it is equal to 1 minus 0, or it is equal to 1. So at t is equal to 1, it is equal to 1. Similarly, at t is, if I want to find r of 2, the limit will be up to 2. So it will be 2 minus 0, it will be 2. So at t is equal to 2, it is 2. So r of t is actually integral minus infinity to t u of tau d tau. The next important singularity function is the unit impulse function. So for understanding the unit impulse function, let us see a general pulse function represented as delta A of t. So which is having a time duration from minus a by 2 to a by 2, and it is having a height of 1 by a. The height of the pulse is 1 by a. This height is 1 by a. Now what is the area under this pulse? If I take this pulse and if I try to determine the area under this pulse, represented as delta A of t. So what is the area? Width into height. What is the width? A by 2 here, a by 2 here. So total of a into what is the height? 1 by a. So which is equal to 1. So this is a pulse with a area of 1. Okay. Now let us say I am making a smaller and smaller. That is, if I keep on reducing the width of the pulse, then what will happen? If I keep on reducing the width of the pulse, that is, I am reducing the value of a, then 1 by a is increasing because denominator is decreasing, 1 by a keeps on increasing. Okay. So let us say this is my pulse with a smaller width. So I am reducing the width. So what will happen to the height? Height of the pulse is increasing. Okay. So this is my 1 by a, because as a is decreasing, denominator is decreasing, 1 by a keeps on increasing. Okay. So but the area remains the same. That is, the width is a and height is 1 by a. So the area is still 1 only. So like that, if I keep on decreasing the value of a, the width of the pulse keeps on decreasing and the height of the pulse keeps on increasing, but area remains the same. What is the area? It is always equal to 1. Now if I make a tending towards 0, that is, I am making a smaller and smaller such that it is approaching 0. Now what will happen? What will happen to the height of the pulse? 1 by a, which is equal to infinity. That means the pulse, when a is tending towards 0, then the width is becoming 0 because a is tending towards 0, the width is 0. whereas the height of the pulse is infinity. The height of the pulse is becoming equal to infinity. Okay, so what we can say here is the width of the pulse is 0 and the height of the pulse is equal to infinity. So here also the area remains the same. So here my area is equal to 1. So here also the area is equal to 1. Okay. Such a pulse, you call it as unit impulse function. So this pulse is known as unit impulse function, represented as delta of t. Okay. So how do you find area in general, width into height, or performing integration between two limits, minus a by 2 to a by 2. Now if you observe these two limits, these two are having 0 in between them. So here also 0 in between them. So here also we have 0. So the unit impulse function can be written as delta of t is equal to 0 for t not equal to 0. Only at t is equal to 0 it is having infinite height, and for other values of t, the signal is 0. Okay, this is 0 here. At t is equal to 0 its height is becoming infinity, and once again it is 0 for t greater than 0. Okay, so delta of t, unit impulse function, can be defined as delta of t is equal to 0 for t not equal to 0, and the area is equal to 1. How do you find the area? By integrating. So by integrating between some limits, let us say I have some time t1 here and t2 here. If I integrate, I am getting the area. So the integral t1 to t2 delta of t dt. So what is the area? It is always 1. Okay. So here t1 to t2 are the limits for time, such that this interval includes the t is equal to 0. So here t is equal to 0. Minus a by 2 to a by 2 is including 0. So t1 to t2 is also including 0. That means t1 less than 0 less than t2. So this is what is the definition for a unit impulse function. Okay, this is what is the definition for unit impulse function. So unit impulse function, we understood it from a general pulse function with unit area, and this pulse is represented as delta a of t. It is having a width of minus a by 2 to a by 2 and height of 1 by a. So area is 1. If I keep on reducing this a value, then width decreases, height keeps on increasing. At when it is becoming 0, width is 0, height is infinity. Okay. So but still the area is equal to 1. So this is called as unit impulse function, and it is defined as delta of t is equal to 0 for t not equal to 0, and if I am integrating between any two limits which is including 0, then it is equal to 1, that is area is equal to 1. So this is what is unit impulse function. Now the unit impulse function and the unit step function, they have certain relation. Okay, so we can write the relation between unit step and unit impulse function. So what is the relation? The unit step function can be written as integral minus infinity to t delta of tau d tau. That is, as I have already told you, the singularity functions are the functions which are related to each other such that derivative or integration of one function gives you another function. Okay. So here my unit step function is written as an integral of unit impulse function. Okay, we can verify it. That is integral minus infinity t delta of tau d tau gives you u of t. We can verify it. Okay, that is, suppose for example, if t is less than 0, t is less than 0 means maybe let us say t is equal to some minus 2. For example, I am taking. So what will be my integral if t is less than 2? What will be my integral? Integral minus infinity to minus 2 delta of tau d tau. Okay, if t is less than 0, for example, let t be minus 2, integral minus infinity to minus 2 delta of tau d tau. But what is delta of t? It is delta of t. If I take the delta of t, it should, the limits in between which I am integrating, it should include 0. Okay, but in this integral there is no 0. It is minus infinity to minus 2 means it is not covering 0, isn't it? That is, if I take this as my time axis, this is my delta of tau and this is tau, and from where I am integrating? I am integrating somewhere from minus infinity to minus 2, but it is not covering 0. I have told you that it is integrate when we are integrating between t1 and t2, it should include 0, then it will be 1. But there is no 0 in between minus infinity to minus 2. So I am integrating in between these two. 0 is out of this interval. So what will be this integral? It will be equal to 0. So for t less than 0, it is 0. Okay. Next, for t greater than 0 or greater than or equal to 0, for example, if I take t is equal to 2, then what will be the integral? Integral minus infinity to t 2 delta of tau d tau. I am taking the next case, t greater than or equal to 0. That means, for example, t is equal to 2. The integral will be from minus infinity to t. What is t here? T is equal to 2 delta of tau d tau, delta of tau d tau, which is equal to, so minus infinity to 2 means it is covering 0, isn't it? Delta of tau, I mean integrating from minus infinity to plus 2, so it is, this interval is covering 0. So if it is covering 0, then it will, integral will be equal to 1. So for t less than 0, whether it is minus 1 or minus 2 or minus 3 and so on, it will be 0. For t greater than or equal to, it is equal to 1, which is nothing but a unit step function, isn't it? We have already seen unit step. It is equal to 0 for t less than 0 and it is equal to 1 for t greater than or equal to 0. So like that, the unit step function is nothing but integral minus infinity to t delta of tau d tau. Now the unit impulse function is satisfying certain properties. So what are the properties of unit impulse function? Let us see now. So the first property is equivalence property. Equivalence property. So according to equivalence property, g of t is some other function. When it is multiplied with delta of t minus t naught, delta of t minus t naught is nothing but delta of t delayed by a time of t naught. It is equal to g of t naught into delta of g of t naught into delta of t minus t naught. That is what is the equivalence property. So let us see the proof for this property. Let us say I have some g of t some function g of t, and this function is varying like this. This is my function. Now I have delta of t minus t naught. As I have told you, delta of t minus t naught is nothing but delta of t delayed by a time of t naught. Okay, so my impulse will be at t is equal to t naught. It will not be at 0. Now when you multiply these two, so my delta of t minus t naught is equal to, is having amplitude only at t is equal to t naught. Outside this it is equal to 0. So when you multiply this, so when t is not equal to t naught, even though this is having certain value, okay, for other than t naught, the product is going to be 0. And only at t is equal to t naught, it is multiplying g of t. So at t is equal to t naught, what is g of t? It is equal to g of t naught. Okay, so g of t into delta of t minus t naught is same as g of t naught into delta of t minus t naught. Okay, because outside this is 0, the product is going to be 0. Here it is 0, here it is 0. So it is getting multiplied with the g of t naught. Okay, so this is what is equivalence property. The second property of unit impulse function is sampling property. Sampling or shifting property. Shifting property. So sampling or shifting property can be proved from equivalence property only. Okay. So let us say I integrate this left hand side of the equivalence property with limits from minus infinity to plus infinity, g of t delta of t minus t naught dt. Okay, I am integrating this with respect to t with limits from minus infinity to plus infinity. This is equal to, according to this equivalence property, this is equal to g of t naught into delta of t minus t naught. So it is equal to integral minus infinity to plus infinity g of t naught into delta of t minus t naught dt. So g of t naught is a constant because we are integrating with respect to t. So it is not a variable. So it is taken outside the integration. So integral minus infinity to plus infinity delta of t minus t naught dt. So minus infinity to plus infinity will be covering t is equal to t naught. Okay, because this is unit impulse is existing at t is equal to t naught. If I integrate from minus infinity to plus infinity, it is having t naught. So because it is covering t naught, it is equal to 1. So this is equal to g of t naught. So integral minus infinity to plus infinity g of t into delta of t minus t naught dt is equal to g of t naught. So this is what is known as sampling property or shifting property. Sampling means I am taking a sample of g of t at t is equal to t naught by multiplying and integrating by multiplying with the delta of t minus t naught and integrating from minus infinity to plus infinity. So we are taking a sample of g of t unit using the unit impulse. That is why this you call it as sampling property, or the unit impulse is shifting. It shifts one of the values of g of t. That is why you call it as shifting property. So these are the two important properties of unit impulse function. Now there is another function which is impulse train. Impulse train represented as delta t of t, represented as delta t of t. So impulse train is nothing but unit impulse, and I am repeating this impulse train, a unit impulse, every capital T seconds. Okay, this is 0, T, 2T, 3T, and so on. So on the negative side, minus T, minus 2T, minus 3T, and so on. So the at 0 it is delta of T. At T is equal to T, so this will be delta of T. At T is equal to T, it is delta of T minus T. This will be delta of T minus 2T, and so on. So here this will be T minus of minus T, that is delta of T plus T. This will be delta of T plus 2T, and so on. Okay, so I am repeating the impulse, the same impulse every capital T seconds. So it is becoming a impulse train. Okay, so impulse train represented as delta T of T can be written mathematically as sigma n is equal to minus infinity to plus infinity delta of T minus nt, isn't it? When n is 0, it is delta of T. N is 1, delta of T minus T. N is 2, delta of T minus 2T. If n is minus 1, delta of T minus of minus T, delta of T plus T, delta of 2 plus T. So when you add all these things, you are getting a impulse train.